Okay, they will discuss the paper published the EPSL in this year, and the title is the carbon budget of Earth's deep mantle constrained by the petrogenesis of silica-poor ocean island basalts, and the authors are Sun and Dasgupta. And then first we look at the first author. The first author, this is Chen Guangsun, assistant professor from the University of Texas at Austin, and he got his bachelor from the China University of Geoscience, Beijing, and he got his master and PhD degree from the Brown University, and then he worked as postdoc at Rice University and calculated with Dasgupta. This work has worked on developing new tools to measure the conditions that were present when rocks were formed. Especially, he has developed a series of mathematical formula. Then we look at this paper. This paper, why they did the carbon budget work, I think there are some shortcomings in estimating. 是我这儿的，好像我这儿的。Estimating carbon content in the mantle source. The first previous study proved that the carbon dioxide shows a constant ratio with some incompatible elements such as NB and BA, but unfortunately, there's no robust carbon dioxide to trace elements ratio for the global OIBs because these such ratios appear too strongly dependent on soil compositions and affected by the degassing. The second shortcoming is previous study almost focused on the subalkalines OIBs, but they overlooking the alkaline OIBs which could choose underestimating of carbon dioxide contents in OIB mantle source. So in this paper, Sun and Dasgupta wanna identify the carbon dioxide to the NB or BA constants ratio and re-estimate the carbon contents in OIB mantle source, considering the alkaline and the subalkaline OIBs. Then besides some study put forward that two models about the alkaline OIBs petrogenesis. The first model is some researcher suppose the alkaline OIBs comes from the asthenosphere, and the second model some support the alkaline basalts come from the lithosphere. So the key point to resolve this problem is to determine the temperature and the pressure of the primary melt at final equilibration with the source mantle. So in this paper, Sun and Dasgupta also discuss the pressure and the temperature of the primary melt. So based on this discussion, they do the following work. First, they calculate the data. They download the primitive basalt major elements components of the global ocean island group from the JORAC database. And this map show us the distribution of the sample. Then they divide the data according the setting into the near ridge and the intraplate. Then according the composition divide them into alkaline and subalkaline series to analysis. Then they do the primary melt correction. We can look at the right figure. I want to say the OIB primitive melt is the collected database, and the target is the primary melt composition. So, as we know, the primitive melts have undergone the variable extent of olivine fractionation or the accumulation. So if we want to know the primary melt composition, we need to add the olivine into back to the primitive melt until the FO equal to 90. Then they get the primary melt composition. Then they use this equation, the function between the carbon dioxide and the silica dioxide to calculate the carbon dioxide of the primary melt. Then we look at some results. Okay, look at those four figures. Those four figures show us the correlation between the carbon dioxide and the NB and the BA in the primary melt of OIBs. The top two are the samples from the interplate settings, and the bottom two are coming from the near ridge settings. And look at the top two figures, we can know the carbon dioxide in the primary melt from the interplate setting displays positive correlation with NB and BA. And we look at the right peaks. Those peaks show us the alkaline and subalkaline results, the carbon dioxide distribution, and the blue and the pink areas represent the interplate and the near ridge settings respectively, and the solid line represent the subalkaline result. And we can see no matter in the interplate or the near ridge settings, mantle source of alkaline OIBs are more carbon rich than those subalkaline OIBs. Then, in order to discuss the alkaline OIBs comes from or their petrogenesis, they need to know the temperature and the pressure of the primary melt. So we mentioned before. So the Sun and Dasgupta use those two equations proposed in 2020 to calculate the P and T, and this result, the left is interplate and the right is near ridge. And we can first we look at those peaks. Okay, the blue area and the pink area also represent the alkaline temperature and the pressure distribution, and the solid line also represents the subalkaline result, this temperature and pressure distribution. And we can say those two parts almost overlap. So the result is that the alkaline or the subalkaline result, they have the same temperature and pressure. Then look at those actual results. This point, we can see those points almost along or below the peridotite solids, and below the CFF, but most important, they are almost below the LAB. So the Dasgupta and the Sun, they spot the first model that the alkaline and the subalkaline OIB is coming from the asthenosphere. Then they, according the result, gave some discussion. First, they propose 3 member scenarios to produce partial melt with higher carbon dioxide contents. We look at the right figure. There are 3 scenarios. The first is the green arrow, the increasing mantle carbon dioxide. The second is a mantle source with lower potential temperature. The last one is the increasing lead thickness. Then they combine those scenarios with the actual result. The bottom 2 figures are the interpolate settings result. We can say in the theory, the potential temperature has the negative relationship with the carbon dioxide in the melt. However, in the actual result, there's no this trade, so they exclude this theory. Then look at the pressure and melt carbon dioxide. The pressure has the positive relationship with the melt carbon dioxide, but in the actual result, there's no this trade, so they also exclude this theory. So in the interpolate settings, there's only the first theory worked. Then compared with the near ridge result, in the first, the actual pressure have the positive correlation with the melt carbon dioxide. This trade coincide with this green arrow. So this theory is worked, and but in those 2 figures, the potential temperature have the positive correlation with the melt carbon dioxide. However, in the theory, it's the negative relationship. So so Sun explained this is combined effect of the increase in mantle potential temperature and the lead effect. Then they fit the carbon dioxide to NB or BA constant ratio according to their actual result. Then last, there are some conclusions. The first is alkaline and subalkaline OIBs are both derived from the plume mantle source. The second is the mantle source of alkaline OIBs are more carbon-rich than those of subalkaline OIBs. The third is global OIBs indicate about 330 to 400 ppm carbon on average in their deep mantle source. The last is the carbon flux from the ocean islands is likely more greater than previously thought. That's about this paper.